Okay, welcome to another video in the Algebra 2 series. Tonight's section will be 6.2, multiplying and dividing radical expressions. Okay. Our objective, to multiply and divide radical expressions. Go figure. Okay. So what we're really going to understand by the time we're done with this section is that we can simplify a radical expression when the exponent of one factor of the radicand is a multiple of the radical's index. For instance, like that. Okay, so we have a square root with an x to the second power. This can be simplified. A third root with an x to the third power, that can be simplified. An eighth root with an x to the 16th power, as long as this is a factor of, or if it's a multiple of the radicand's index, we can simplify this expression further. Okay, we can also simplify the product of powers that have the same exponent. For instance, these two have the same exponent. We can simplify this to 2 times 3, both to the second. Okay, works with radicals for any expression. Okay, so let's get into it a little bit. Okay, so our first property is combining radical expressions, the product property. Right, so if the nth root of a and the nth root of b are real numbers, then the nth root of a times the nth root of b is equal to the nth root of ab. Okay, this basically says that if you have the same index, you can multiply these two, the numbers underneath the radical together. Okay, as long as you have the same index, you can combine it into one. Now, there's a very important part of this property, and that is that it assumes that these two are real numbers. Okay, that is extremely important, and we'll talk about why in a second. But first, let's try to use this thing a little bit. Okay, can you simplify the product of the radical expression? And explain if you can't. So, you might be tempted to say that this is a root of 12, but because the index is different, remember, if you don't see it as a 2, because the index is different, there's nothing you can do here. This is as simple as you can make it. Okay, so for part A, the answer would just be the third root of 6 times the square root of 2. You cannot put those two together. However, for part B, because they're both the third root, we can simplify this into the third root of -8. And then I can decide if the third root of -8 can actually be simplified anymore. And it can. -2 times -2 times -2 is -8. So the answer for that is -2. Okay? So let's try these two with our got it problem. Can I simplify the product of the radical expression? These two, ooh, wait. Well, that is the fourth root of 7 times the fifth root of 7. Now, there is a way that we can put those together. We just don't know it yet. Okay, so for now, we're going to say not yet. Okay, but there is a way to put these together. These ones, however, are much easier. It just simplifies into the fifth root of 10. And can I simplify the fifth root of 10 anymore? No, there's no number that multiplied by itself 5 times gives you 10. Okay. Before we jump into that, right, we should remember how to do this, right? If I want to simplify the square root of 8, we would break this into something that's a perfect square times something that's a perfect square, and we would get 2 square root of 2. That is different than what I do with the cube root of 8. Now I'm not looking for perfect squares anymore. Now I'm looking for perfect cubes, and this just simplifies into regular 2. So these are obviously different. Okay, so when we're looking at the simplest form, when we're trying to reduce a radical expression, we have to look for perfect nth powers. And what is n? Well, it can be anything you want, right? We're going to probably stick with 2s, 3s, and maybe 4s in our course here. But we're always looking for that thing, right? That perfect cube, that perfect fourth, that divides into a to see if I can simplify this anymore. Another example with a square root and a cube root, the square root of 24, well, 4 is a perfect square that goes into 24. So we can simplify that into 4 times 6 to give me 2 radical 6. However, with the cube root of 24, I don't want the 4 anymore. I don't want the factor 4 times 6. 4 is a perfect square. It's not a perfect cube. However, 8 is a perfect cube, and 8 does go into 24. So now we see that my answer is 2 cube root of 3, okay, in the simplest form. So a much different approach when you are simplifying a perfect square. We use squares. 4, 9, 16, 25, right? Perfect squares. Whereas cubes, we use 8, 3 to the third is 27, 4 to the third is 64, 5 to the third is 125. We use numbers like that that go into the thing that we're trying to simplify. Okay. So, what is the simplest form of this expression? Okay, so let's break it down a little bit. The number and the variable. 54, okay? The largest perfect cube that goes into 54. Well, what are perfect cubes? 2 to the third is 8. 54 is not divisible by 8. 3 to the third is 27. 54 is divisible by 27. It's 27 times 2. Okay, maybe there's another one. 4 to the third is 64. That's too big. That's not going to go into 54. Okay, so here's my guy. There is the biggest perfect cube that goes into 54. So I break this equation into 27 times the cube root of 2 times the cube root of x to the fifth. We'll get to the variable in a second. Okay, let's focus on the numbers first. This is 3. 3 times 3 times 3 is 27. This, the cube root of 2, does not simplify. So we just leave it as 3 cube root 2. And now we got to deal with this. Okay. So as long as the exponent is a factor of that, I can simplify this. 5 is not a factor of 3. But I can separate this just like I did the numbers. So we're here, and I'm going to separate the x into x to the third times x squared. 3 and 2 give me 5. The third root of x to the third is just x. So now I write my answer as 3 and x, because those are the two things that came out of the radical, and the leftover inside is 2x squared. And I finished this off with something that we did last section, is that the even, odd rule, if it applies, we need to put absolute value signs around my variables. Luckily, the exponent or the index is not even. It's odd, odd, odd. And it's weird we have 2 of them. So we'll look at that a little bit later. Okay, let's try this again. 128. If I look at my perfect cubes there, ooh, 64. 64 times 2, oops, 64 times 2 is, there we go. 64 times 2 is 128. So we split that into the third root of 64 times 2 times, let's just split x to the seventh. I need it to be a factor of 3. Well, x to the 6 is a factor of 3. And I have 1 left over. I want the biggest factor of 3. I could have split this into a 3 and a 4. But I don't want to. Okay, I want to take as much out as possible in order for you to for it to be simplified. These two terms can come out of the cube root, and I take the cube root. So the 64 turns into the thing that multiplies 3 times to give you 64, a 4. X to the 6 becomes x squared, the 6 divided by the 3, and we're left with 2x. Right? And anything that comes out of a radical, I always write it first. If I didn't, right, if I had the third root of 2x and I put the 4x squared there, it can be tough to tell whether or not the 4 is outside, whether it's inside. If you want to be sure it's outside, you got to put weird parentheses like that. That's weird. Don't do that. We're just going to put it right out in front, so that way it's understood that it has now come outside of the radical. Okay. This can get slightly confusing now. Okay, so problem 2 involves simplifying a cube root, so absolute values were not needed, right? Even odd rule. We have a cube root. That's an odd, so we didn't need it. Okay. Remember that when you combine these two by multiplication, both radical expressions must be real numbers. Remember how I said this? That one of the most important parts of this theorem right here was that they're both real numbers, that both the two things that you are combining using the product rule are real numbers. Well, the only reason that we use a radical expression, or sorry, the only reason that we use the absolute values in a simplifying radical is to show that those numbers must be real, that they must be positive. Okay, absolute value numbers become positive. So that means that if I use the product property, I never need absolute value bars. Okay, so let's take a look at this with this new problem. Okay, so first let's simplify it and then let's talk about what happens. Okay, they're both square roots. I can put them together. Okay, so let's do that. So I'm going to take this and I'm going to do 72 times 10, 720, x to the 4th, y, add the exponents to the 5th. Okay, so this is square roots. I need a perfect square factor that goes into 720. And if you're not sure what it's going to be, you could use prime factorization and just count up all the pairs. But I can tell that 144 times 5 is 720. So I'm going to split this into 144 times 5. I can leave x to the 4th. This has to be divisible, right? It has to be a factor of 2. So I'm going to make it y to the 4th and one more y. That stays behind. That stays behind. I can take the square root of all the other terms. Square root of 144 is 12. The square root of x to the 4th is x squared. The square root of y to the 4th is y squared. And we're left with a 5 and a y. Okay. Even, even, even. You would think I would not need absolute value bars. And you're right. Even, odd, even. I wouldn't need it. And you're right. But because my first step was to put these two products together, I would actually never need absolute value bars. Okay? So that's an important distinction. Okay? So let's try this one more time. Okay? So what's my simplest form there? So we put this together with 45 times 35, and I have the square root of 1575 x to the 6th, x and x, y to the 7th. Okay? The square root of 1575, what can that possibly break it to? Well, I'm not really sure. I could do it on a calculator, but I definitely see that it ends with a 75. So I could always divide out a 25. and that gives me 63 times 25. Can you break a 63 into something that is a perfect square? 9 times 7 times 25. Okay, so that's a 3, that's a 5. When you bring it out of the square root, that gives me 15. And it just happens that 1575 is 15 times 7. Okay? No, not quite. 15 times 15 times 7. So, yeah, 225 times 7. But that's tough to see just by looking at it, right? So, you could always break this down into other perfect squares. X to the 6th comes out as x to the 3rd, and y to the 7th, we break that into y to the 6th and y. Y to the 6th comes out as y to the 3rd, and we're left with x, no x's, 7y. Okay, let's look at my even, odd. Okay, you would think that, and this was even, odd when these were together, so you don't need it right there. But you would think that you would have to put absolute value bars around the x to the 3rd. Okay. In this case, you do not, because the first step was putting those two radicals together with the power rule. Now, here's the weird part. If the problem started there, if the problem just said simplify this expression, okay, with, and let's put this back the way it was, like that. If the problem said simplify this expression, now did not start there, right? You didn't use the power rule. We're starting right with this expression right there. Now you do need absolute value bars around the x. Some texts will tell you to put it around the y. I say that you don't need to because you're leaving a y underneath the radical, which implies that the y cannot be negative or you will get an imaginary number. Okay, but now we have an even, odd. Even root of an even exponent that gives you an odd number exponent. An odd number exponent in your answer. So if you remember from 6.1, I said I was going to add to that even, odd rule. So it's an even root of an even exponent that gives you an odd numbered exponent in your answer, as long as you never use the power rule or the quotient rule, which we'll talk about in a little bit. Okay, so once you use this rule, once you put these two expressions together using the power rule, okay, once you put them together, now we no longer need to worry about absolute values. So that's probably the most confusing part of this chapter. Speaking of division, let's do a little division. Okay, so suppose you define division in terms of multiplication, which you should. You can extend the property for multiplying radical expressions. If the indexes are the same, you can write the quotient of roots as the root of a quotient. The quotient of two roots as the root of one whole quotient. As long as you both have square roots, as long as you both have third roots, you can put them together, just like you can with multiplication. And again, as long as these are real, so as soon as we use the power rule, as soon as we put these two things together, we no longer need to worry about absolute value bars, okay? And now we get our expression with the same index with a over b. Okay, so as long as they have, what's the simplest form of the quotient? As long as they have the same index, which they do, okay, we can do this as one expression. 18x to the 5th over 2x to the 3rd, and I can simplify that. 18 over 2 is 9. And x to the 5th over x to the 3rd, subtract the exponents, and you get x squared, which gives me 3x. Even, odd. I would need absolute value bars, but I use the quotient rule, so I do not. Okay, Again, if the question had started right there, if the question was simplify 9x squared, then you would have to put an absolute value bar. But in this case, because we use the quotient rule, remember that we do not need to do that. Okay, so both third roots, which means I can put these together. 162 divided by 3 is 54. That works out nicely. Y to the third. 54 we just did before. 27 times 2. So we can split this into the third root of 27 times 2 times y to the third. Cube root of 27. This one is the only one that stays behind. The 27, the y to the third are both perfect cubes, which gives me the third, no, sorry, which gives me 3y cube root of 2. This is not an even root. It's an odd root, so I never need absolute values, and I wouldn't have needed it anyway because, what did I start with? A quotient. Okay. Let's try part A first. So we have the square root of 50, x to the 6 over 2. Well, first thing I'm going to do is I'm going to put those together. 25x squared, which gives me 5x. And because I started with the quotient rule, I don't need the absolute value bars. Can you simplify the expression in problem 4a, back up here, by, back up here, the first one? Can I simplify the square root of 18 and the square root of 2 first? Well, no. The square root of 18 doesn't really simplify. It can simplify. Okay, you could, okay? So if we started with this, we could have taken 18x to the fifth over 2x to the third square root. I could have simplified the square root of 18 into 9 times 2, which is 3x squared square root of 2x over square root of 2 doesn't simplify, but I could simplify this into x square root of 2x. These two would then cancel. One of these would cancel with one of these, and we'd have 3x. So the answer is you could, but it is much, much more difficult because now you have radicals canceling with radicals and things coming out and things staying behind in each one. Best to put them together first and make the question easier. Okay. Another way to simplify a radical expression is by doing something called rationalizing the denominator. Okay, we do not leave radicals in the denominator. So, whenever we have a radical expression that has a radical in the denominator, like that, we always strive to get rid of the radical in the denominator. Okay, now when it's a square root, it's usually pretty simple. Okay, we multiply the number by itself, and that gets rid of the square root. So we're always going to multiply the top and the bottom by the same thing, so that way we don't change the expression. We're multiplying by 1, so we're keeping it the same. But in the denominator, right, radical 2 times radical 2 is radical 4, which is just 2. So it's usually pretty simple when we have a square root. Where this gets a little crazier is when we have a cube root, right? So here, we're trying to complete the square, right? So if I have a 2, the number that completes the 2 is 2. But if I had the third root of 2, the number that completes this third root is a 4, because 2 times 4 is 8. That is a perfect cube. If I just multiply the top and the bottom of the expression by the third root of 2, same thing, I would get the third root of 4, which is not a perfect cube and therefore does not get rid of the radical. Let's try it. So what's the simplest form of this expression? Okay. Now, before I do anything, I should try to simplify this. Can't simplify it. X, Y, Z. Okay, nothing I can do. All right, so I want to break this down into its perfect square factors to see if you can get sort of a look at how this works. Okay, and because I have this all one expression and now I can't simplify it, now I'm going to split it back up. Okay, and the third root of 12y squared z. Okay, but I want to break this into perfect, into its prime factors. Okay, so 12 is 4 times 3, which is 2 times 2 times 3. So we have 2 squared times 3 times y squared times z. Okay. This this form now makes it a little bit easier for me to complete the perfect cube. If you wanted to, you could take 12 and multiply the top and the bottom by 2 more 12s, by 144. Okay, but that's not the best way to do this. Okay, so the numbers that I should take and multiply the top, remember I have to do the same thing on the top and the bottom, is whatever number completes a perfect cube. I have 2 2's there. I need 1 more. I have 1 3. I need 2 more. I have 2 y's. I need 1 more. And 2 more z's. Whatever I do on the bottom, I do on the top as well. 2 times 3 squared yz squared. Okay, why did I pick these numbers again? Because they make 2 to the squared times 2 is 2 to the third. 3 times 3 squared is 3 to the third. Y squared times another y is y to the third, and z to the third. Okay, so I picked those numbers because when I multiply all the numbers together, I get a perfect cube. So watch. We have, this is 12, right? 2 times 4 times 3, 12, times this stuff over here, times 2 times 9 gives me, on the bottom, the cube root of 216 y to the third, z to the third. All of those are perfect cubes. Now on the top, I don't care what I have on the top. 2 times 3 squared, so that's 18 times 5. That gives me 90 x squared y z squared. Okay, and I finish by x squared y z squared. I finish by taking the perfect cube of all of these. That's 6. Ooh, ugly 6. That is 6 y z. Okay, so what we just did was we got rid of all the radicals in the denominator. We rationalized the denominator by multiplying the top and the bottom by the thing that made the denominator not a radical anymore to make it into a perfect cube. This one was actually a little bit harder than our next problem. Okay. So this problem a little bit easier. The third root of 7x over the third root of 5y squared. This one's easier because 5 is prime. Okay, so it's pretty easy to figure out the number that I should multiply the top and the bottom by to turn 5 into a perfect cube. Well, 5 is prime, so I just need 2 more 5s. So that would be a 25. 5 times 25 is 125, which is a perfect cube, and I need 1 more y to give me 3 y's. Got to do the same in the top and the bottom. 7 times 25 gives me 175. X and a y over 5 times 125 is 120. We'll write this out. 125 y to the third, which gives me 5y on the bottom. Okay? And this one makes a little more sense because these numbers match up because I'm using a perfect cube. Okay? So, uh, so uh, hopefully we would have no problem doing anything like this. These two can go together, so can these. These two cannot, and these two can, but look at that. It won't simplify because there's a negative underneath the radical, which means we would get an imaginary number. Okay? These we can divide and simplify. Write the simplest form of this. That should be no problem. Right? Third root of 32 would be, we'd split that into 8 times 4 times x to the third times x. This and this come out. That one and that one stay behind to give me 2x cube root of 4x. For what values of x is this real? As long as x is a negative, then this is negative times a negative to become positive. Okay? And never do this. Never subtract. I take that back. We can do something with this. We're just not there yet. But it's not this. Okay, so that's not right. Okay. So hopefully there's not too many questions. And that was 6-2, multiplying and dividing radical expressions.